let me first, before I prove another proposition, fix an important typo, and more importantly, even to change the definition. So the definition I showed was the definition following Dasgupta and Maskin, which is a classical paper, but that definition is not the best one for our purposes. And there are many definitions, as some papers note that. So basically, I don't want to go into the multitude of the definitions for the general games, I mean n-player games. I just give you another definition, which is better for our purposes. It's not so crucial for this course, so that's not so important, but I will give another definition. One remark that for two players, the definition coincides with what we did before. So the utility of player 1 when they played S1 and S2 is the same as the utility of player 2 when they played S2 and S1. So when I play one, I, like myself, play S1 and the other person plays S2, I get the same. It does not matter whether I am player 1 or whether I am player 2. That's what it means. Now for M players, the definition that I want to give is a bit different from what we gave. First of all, of course, the permutation has to go to work on the player and not on the utilities. Not on the strategies as it was written before. It was simply a typo. But more importantly, we need to permute players by a given permutation and the strategies by the reverse permutation. That's something which is crucial. Let me explain. Well, the definition is as follows. Given an n-player game, it's symmetric if the strategies of all the players are the same as said, and for every permutation, a permutation is a bijection, one-on-one and onto function, permutation of the player, for every player, and for every strategy profile S1 to N, we have the utility that player I gets when the profile is S1 till Sn is the same as the utility that player Pi gets when the strategies are Pi, the reverse P, so P in the power of -1 of Y until P in the power of minus I of N. So that's the counterintuitive maybe thing, that we permute the player with one permutation and the strategies with the opposite one. Of course, permutation as the bijection always have the inverse function. Now, why do we define this network? Actually, that makes sense. Just look. That's a confusion of permutation. What we want to say is that, what we want to express in this formula is that the utility of player I is the same as the utility of a player Pi, provided that the players do the same. So the player Pi has to do the same what player I did before. So the strategy of player Pi has to be the same strategy of player I. So it has to be reversed. It has to be the same as P minus 1. And for any other player, the same. So if any player J, the strategy of player J we want to see here is the reverse, because we want to see, okay, what did that player did before? Because every player after permuting by P has to see what the respective original player P minus 1 on that saw before. That's the logic. Now, given that, all this statement stay the same with the same proof. So the definition of a symmetric profile is the same, and a symmetric profile always implies that actually, yeah, it implies that the utilities or applies to the utilities of all the players in that profile are the same. For two players, as I said, the definition looks the same, the examples stay the same. They have for two players, the existence proofs, statements and proofs stay the same. Now, the last thing about symmetry here I want is to mention an important simple proposition which I formulated on the tutorial. But since I looked at a different definition, it didn't work. But that should work for a reasonable definition, which I state is the definition I just gave. And that proposition is as follows. If a game is symmetric, then for any permutation P, a profile is a Nash equilibrium if and only if its permutation, so S of P1 and so on, when the ith player basically does what the Pi player did before, that's to a Nash equilibrium. So I'm not claiming there is a Nash equilibrium, but one is if and only if the other is. The original profile, one profile is if and only if the permuted profile is, and that's true for any permutation. So we can basically say that an Nash equilibrium is a set of strategies which are played, and multiset perhaps they're the same. You can just say each strategy how many times it's played, and we don't have to say where they are, because for the sake of being in an equilibrium, that's the same. Now why? And the proof is quite simple again. It's a bit confusing because of those permutations. Now, but it's very simple. So the original profile is an Nash equilibrium. That's what we assume. Because we assume the original one is, and then prove that the other one is. The other direction is the same because permutation is just, we can just prove the same with by p in the power of -1. So the original profile is an Nash equilibrium if and only if, by the definition of a Nash equilibrium, for any j and for any deviation for the player, the utility of j in the original profile is at least as what j gets when sj changed to the deviation and the rest due to what they did before. Now, given any player I, now we prove what we need. So given any player I, and let take I to be the p-1 of j. The g is a pi. Because we are given I actually should say no. We know what the above for any j. So let j be used pp of I. Given I, let j be used in this inequality pp of I. And then the symmetry definition, which we saw, which we bring here for a reminder, when we apply it with p minus 2 to the power of -1, implies that, by definition, that the utility here I imply I enact P, here I enact the reverse. Now here I begin with the reverse, so here I enact the reverse, and here I enact P. And that, so I enact the definition on this inequality, which we know to hold, and therefore I get the u of p-1 j of the profile permuted. Pay attention here, it's permuted by the original, not by p-1, because I started with the inverse permutation. That's at least, now I enact this permutation equality on the other side of inequality, and I obtain that is at least that. Now what's that? The same, only that Sj now in the original inequality we see that Sj has changed to something else. Sj, we call it in the new proper the deviation Sj prime. Now we apply p-1, and since it has to be -1 in the definition, we just apply p on j. So we just apply P. Now, no, not on J. We apply P on everything. Now, the actual player whose profile changes is the player whose P becomes J. Let me repeat. We take this profile and whatever any player did, so now this player does what the player P of this player did. Now it means that relatively to the what then this deviation means? The player whose P is J, that player changes. Now, which player P is J? P of I is J. So P of I changes. So it's important to understand, it's a bit confusing. So the player whom permutation P brings to whatever strategy player J used to do, that player does something different with respect to this profile. And that player is by definition of P is the player Pi. Now that means when we replace by the definition of P again, P minus 1 of J is I. We basically say that the utility of player I in this profile is at least as what player I get when it follows this profile, whenever it follows this profile besides that player. And that means that this profile is an equilibrium. Okay, so that was it. The last thing we are going to tell now, for now, about symmetry games, but mostly we will deal with two-player symmetry games.